so happy that a lot of people can join us. I'm Carl Eriksson. I come from Svenska Elektrod, and we are the distributing partner of Olympus A&I, specifically for XRF and XRD equipment in Sweden and Norway. We have our head office here where we are right now in Täby, outside of Stockholm, Sweden. And apart from being a distributor partner for Olympus, we're also a certified system integrator for Universal Robots. And that's actually what this meeting will be about, or this presentation. I'll be showing you both the UR arm. So this is a cobot arm. I'll be talking a little bit about this in specifics. But what you're all here for and what you want to know more about is this guy, the Vanta Ix, and how that can work in different integration environments. So I'm going to jump right into it. This guy is Vanta Ix. And for those not familiar with the Vanta series of XRF instruments, this is Olympus renowned instrument series that builds on the Axon technology, which gives us rapid testing and very, very, what do you say, vad säger man när man säger repetitive results? Yeah, so very stable results. Yeah, thank you. This is now an adapted version for integration purposes. So what you can see directly is you have these small bolt holes, because right now we put it on a cobot arm, but we might as well put it in any other kind of integration setup. So we can use either these M4 bolt holes on the side here. We have M4 bolt holes on the sides here, both sides. And we also have them on the back, which is what I've been using now when I've attached this 3D printed faceplate to attach the Vanta Ix to the cobot arm. Now keep in mind, as you see, this is plastic. This is something that we just drew up and 3D printed to have like a setup just to prove the concept and to make sure that everything works. Now, if we look at the front, we have a faceplate which is really swiftly interchangeable. You just have this clasp release here, which enables you to open up and change the protective film. And if we look at the back, we have a number of inputs and outputs. So right now I'm powering this device through an Ethernet connection. And this is really the preferred way of doing it, because then we have both the data acquisition and the power in one unit. Now, the unit draws 30 watts, so you need to have what's called the PoE plus, the power over Ethernet plus. A standard PoE doesn't cut it. It's not enough. If we look at this port, this USB port is mainly for configuring the instrument if you want to use it in a headless configuration. So what's a headless configuration? Well, that's a configuration where you don't have any screen attached to it. You don't have everything is kept within the instrument. So you have no way of communicating with it either other than connecting it back online or anything. So you cannot monitor it while it's running. That's a headless setup. What we got it sitting in right now is not a headless setup, because what we're going to be showing you a little bit later, we can actually control it via the standard Vanta Desktop App that you're used to if you're using the Vanta instruments. But this one is, of course, adapted to the Ix. Now, we have a couple of other inputs. If we're running it headless, not using the power over Ethernet, we need to power it otherwise. Or if we don't have a power over Ethernet compatible switch, we need to power it via standard DC 18-volt power. That's what we get in here. This guy over here is the connection for the lamp, the warning light sitting over here that you'll see blinking when we're doing testing with it. So this needs to be connected in order for the system to work. Now, all the wiring that you see here today is more or less just a proof of concept setup. So, I mean, you need to think of it in a production environment where we have pre-made real cables, so everything is drawn perfectly. As you see, we've just used zip ties and some 3D printed scaffolds to just hold everything in place. But keep in mind, this will of course be a finished product once you have it in production. So we have two more ports here on the backside. We have this one and this one. These look exactly the same, but are actually very, very different. This one is the Olympus GPIO connection. So GPIO stands for General Purpose Inputs and Outputs. And Olympus has a factory pre-configuration of different stuff that we can do with the Vanta Ix. So we can start a test, we can listen if the instrument is ready, we can tell someone that we have radiation on, we can provide an interlock signal to say that the instrument is in place or the part is in place, etc. So we can communicate with different automation protocols. So what we're using today is the PLC from the cobot arm from Universal Robots, but we might as well communicate with any other automation system that you already got in your factory. The other one then is the other general purpose inputs and outputs, but it's for customer specifics. So if you want to have very, very reliable determinations of whether it's, for example, if you want to sort out alloys, you want to sort out 316, then we could have a signal that if this alloy is 316, then send an output, and then we can make determination based on those. And all those scripts are in a little catalog in the Vanta, so it's actually very, very simple Python programming. So if you have automation engineers that are used to Python programming, that's really convenient to use. So depending on what you actually want to do, what you want to use to determine results, etc., you can do it very, very simple like that, or we can use the Vanta API. So there's a application protocol or programming interface with the Vanta where we can connect it with the Ethernet port and then just send requests. So we're using Java and JSON to actually communicate with the Vanta and send and receive signals, start testing, receive full results, determine, etc., and send results over the server. So we can do all sorts of things. Now, the way we've configured it now is that we've actually just we've communicated two things from the Vanta to the robot. So we're starting tests, and we're listening for if the unit is ready. That's the only thing we've done today. And Ludwig, if you go to a screen where we show you the different ways we're communicating with it right now. No, not that one. Not that one. Not that one. Another one. Probably, no, all the way down. All the way down. It's called like run test. There we go. So what we got set up now is a just a simple pattern sequence where we have 5 different objects in a line. The only thing we did was we told the instrument where this one is, we told it where the last one is, and then we said that it was 5 different samples and what it was going to do at each sample. So that's what we're going to be doing. I'm going to show you also the programming to let you know how it works. And if you look at the screen, you have on the right-hand side the Google Chrome window is actually looking at the listener service from the Vanta. So this is typically what you'd set up to have in your production environment next to your station. So you can live monitor what's happening in the instrument right now. On the bottom hand left side of the screen, you have the Vanta Ix Desktop App. So you'll recognize that if you are familiar with the standard Vanta instruments, it's the same. You have the menu tray and you have the application tray, and you can go through and set up all your different parameters, etc. So what we're showing you today is a very, very simple, not laid out at all exercise where we're just going to show you when we're using the instrument in a standard, easy PLC configuration. So we haven't prepared like perfect libraries or different samples that are perfectly laid out. So we're showing you something that we basically set up in 5 minutes. Keep that in mind. Ludwig, if you change to the programming screen. So here you have, on the right side of your screen, you can see the actual, or can you?
Yes, they should.
No, they're not. They're not. They're just seeing a static. They're not seeing the programming screen, actually. Why is that? If you go into OBS and you go to, you right-click that, Egenskaper, and then you choose the HD60S, so you choose it again, and then click OK. So that's a bummer. Yeah, okay. So let's set it up like this instead then. Go to my little mobile camera. Yeah. So now you'll see, anyway, what we've set up is a little program where we've actually determined these positions. So we can actually move to this item, moving the robot there. So we've determined that first position. Then we have determined the last position. Let me just move up a little bit so we don't hit anything. We move to a last position. Whoop. Let's see, so we don't move them out of place right now. There we go. There we go. So we told them that last position as well. And then everything in between, the program itself has said, we've said that it's 5 items. So imagine you'd have a series. We want to do a, for example, a rock tray in a mining application. Then we'd define the different rows, and then we define how many points in each of the rock trays we want to try out. And then the Vanta would do all the testing for us. So let me just run this, and we'll talk you through what you're actually seeing. So you can define programs and you can save them. So this one I've called Vanta Ix Demo, and we can run it from the beginning, and you'll see what happens. So now the Vanta is running tests. It's running the first position tests, and you can see on the warning light that it's lighting up to tell it that it's emitting radiation. So now it's emitting radiation, and it's actually waiting for the signal that it's done. Then it moves to the next location to make sure that we have all the different tests. So this is a very, very simple sequence. We could also involve a fault. So for example, if there is any error with the Vanta instrument, we could tell the program to move to a specific position, etc. We can have other lighting, so we could have a big light in our environment where we're running the tests, and we could have, depending on the actual sequence or what's happening right now, we could have different lighting showing up. But basically, any possible configuration would be possible. Now you'll also see on the right-hand screen that you have a you'll have a live feed, which is the listener service on the web page. And you'll see that that's lagging a little bit. On the bottom hand left side of the screen, you actually see the Vanta Ix Desktop App running the tests live. So basically what it's doing, if you're looking closely on the bottom left hand screen, you have that little play icon. What we're actually doing is more or less pushing that play icon, but we're doing it with the PLC from the robot. And this could be done with any kind of PLC that you have in your automation. And what we're seeing right now, as I said, this is just a standard line sequence with 5 different samples. We could have this in this kind of position, or say you have samples that are hanging from the ceiling. You could easily do this programming in another plane. So you'd have a matrix of different sample positions on a hanging sheet of metal, for example. This would be easy to do in any other plane. And also, what you're seeing right now, the robot is sitting on a level surface. Well, in this case, it's on a carriage, but we might as well put it in the roof or in the ceiling or on the wall. And if you have samples that are moving on a conveyor, you could also hook up the conveyor signal to the robot so that you program this kind of setup where it's supposed to do testing, and then you program with the conveyor signal, so it's actually doing conveyor tracking. So the movement of the robot will be relative to the conveyor at all times. Yeah, Ludwig, have I forgotten anything?
I don't think so. Covered it mostly.
Cool. That was fast. Yeah, I'm actually going to open up to questions. Damian and James, do you have any specific things that you're wondering for maybe your customers or your applications where you want to ask of our experience with the Vanta for the time that we've had it?
No, I mean, Karl, I mean, yeah, I would like to thank you for this demonstration. It's quite amazing and fascinating. You can see, I can also hear that, yeah, you had a lot of fun playing with this kind of toys. No, I think it's, yeah, you highlighted most of the nice features. I think it's yeah, this is a kind of tool which opens for a lot of opportunities and has a lot of flexibilities.
Yeah.
Certainly in terms of data processing and export and so on. I mean, it's yeah, it's great. So yeah.
I mean, so the 2 basic features that are really standing out here, and what we're really the possibilities is that, you know, the manual sampling with XRF, it's tedious, it's boring, and it's also putting the manual error in play. So we always have some kind of manual handling, and that'll end up screwing up your data set if you do something wrong. Here we know that we're doing the exact same thing over and over again. So that's of course the benefit, but also where we can, if we think a little bit ahead, we can actually do, you know, determination in our production. So if we're doing, I mean, the Vanta can be used for coating thickness, for example.
Yes.
So if we have a circular tree of a electroplating application, for example, and we want to determine the thickness of that layer, and then maybe run it an extra time through that carousel because we want to have a higher one, then we can actually automate that with an XRF rather than doing sheet thickness measurements manually and then determining that. So we can actually build that away.
Yep.
Yeah, James, any inputs?
Yeah, echo Damian's sentiments. Thank you for the demonstration. It's cool. One of the questions I wanted to ask that I guess I asked a lot is, what's the kind of maximum speed that the arm could run at? So if you were running in line with a conveyor, for example, what kind of speed can the robot arm manage?
Yeah, so depending on when you use these kinds of collaborative robots, you'll be talking about something which is a collaborative application or which is a classic industrial robot situation. And the classical robot situation requires fencing, requires gates, etc. So depending on your application and where it's going to be sitting in your production, you might already have that fenced, and then the robot arm could be moving in full speed. And the full speed of the UR cobot arms are roughly 1 meter per second, so it's fast. We can throw a baseball with it. Now, in a collaborative situation like this, we are limited to 250 millimeters per second. So it's basically the speed of a hand when you're doing stuff. That's basically what you can do. So 25 centimeters per second. That's the limit in a collaborative application. Mm-hmm. Then again, I mean, I'd say that since it's an XRF, even though we use it manually, I wouldn't say that it's going to be a collaborative application per se, but I wouldn't tell you to collapse it in too much either. So if we have a rock tray application, for example, in a core drilling facility or a core library facility, and we want to do core tray examination, I mean, you could have a little sensor on the conveyor that's transporting the core tray. You could have a stop, and then the Vanta could do all the sampling. Then the conveyor could transport it to the next and moving up the next rock tray. And that would still be, a collaborative, like sort of collaborative application. So you always need to think of, is the automation going to be in danger of people or not? That's basically what you want to know.
So I was thinking at a previous organization I worked with, they made components for gaskets, producing around, I think it was about 3,000 per day.
Yeah.
Which would all be automated, and then a person would turn up and manually handheld XRF gun every single ring.
Yeah.
And I'm thinking, so I'm kind of thinking, if those gaskets are falling off a train onto a conveyor, how quick could we go?
Yeah. I mean, basically that's also, I mean, basically what we could. I mean, you need to be looking at how fast could you do it with the Vanta. I mean, this Ix is a Vanta C Ix. If we'd have a Vanta M Ix, we would be much faster. And we can also, I mean, optimize the calibration for the application. But basically, I'd say that the limit will not be the movement speed. The limit will be the XRF testing speed, rather. Because if we look at this arm now, this is the one with the biggest reach from Universal Robots. So this has a 1,300 millimeters reach from the base. So you can do a 2.6 meter diameter, 360-degree revolving. So if we put this above somewhere, we have a very, very good reach over an application area. But yeah, in that case, with those gaskets, I'd probably say that they should be moving them into, some sort of palletizing sequence or a pattern. And then when the robot says that I'm done with this lot, it's just moving it down and filling up a new tray or something. Or you wouldn't even put it on a robot. You would actually have it so that all the little gaskets stop on top of the Vanta. So the Vanta sits beneath, and then when the Vanta tells you I'm done, it will send on and then take the next one. That's probably what you're going to do.
Yeah, I think there's many potential applications for how the IX could work, the Vanta Ix could work, and from our perspectives as well at Olympus, I think one of our greatest difficulties has been kind of understanding the potential integration options. And one of the best things I like about what you've been doing with it is that it's kind of opened my eyes to, it's not the Vanta being sat stationary anymore, which is something that historically is what we've kind of done with previous products. So the ability to bring the analyzer to the sample, but automated is it's quite appealing. It's definitely eye-opening.
And I mean, the cool thing about that is that, you know, previously all automation instruments have been quite fragile in terms of movement, but now with the Vanta instruments, the electronics are so stable and rugged, so they can actually, it doesn't matter if you move them fast, it'll cope with it. So yeah, I mean, that's why we actually can put it on a robot arm rather than have it in a stationary automation environment. Vladimir, you raised your hand.
Yeah. Hi. First, also
Hi.
thanks a lot. It was great, absolutely. I just wanted to ask a couple questions about the ability to add kind of proximity sensor on the robot arm to understand when we're, because right now you manually like decided, okay, it will be this kind of gap between sample and the probe head. But when you talking about the speed of testing, it's also the thing we have to consider, how close we are. So how difficult is this? I know that it's possible, but how difficult and how much it's more costly in case of like.
So actually, it's super easy. I don't have that kind of sensor here right now, but what we would do, I'll just stop this so I can show you. Let's see, I'm just waiting for it to stop testing. There we go. I can show you, and I'll do it like this so it goes a little bit faster. So what we would do is that we would put in here, in between the Vanta and the robot arm, we'd put what's called a force torque sensor. So what we then would do is that we would tell the Vanta to, okay, this is the position, but every time in the position, you should be approaching the object with a certain speed. And once you feel that you're touching the object, then you should stop. So that's what you do. So this kind of pattern, like for example in a rock tray, that would be perfect, because sometimes it's a little bit uneven, you don't know, and you want to have it very stable, sitting in the middle of the rock tray. Then we could actually use this force torque sensor in that way to really just go down and feel the sample, and then nudge off a little bit and take the sample, because then you know that every single position is the same.
And also just like because you're already like absolutely in display and you can feel it and like get the results and so on. So of course we face a problem with and not only us, like every single piece of equipment who do this kind of test on the line, when we test only a small spot, and how difficult will be, for example, to align couple units together. So I mean that, for example, we have any kind of let's say plate. And we don't have enough time to do this consequence tests one by one, but we want to do them automatically let's say four. We have 4 robo arms, we have 4 Vantas. How quick we can make an average through these tests as a result? How do you think, from the coding perspective?
So I mean, in that case, you'd have to have we would have some sort of intercommunication between the different Vantas, because in that case you would be sending all the data directly into some sort of cloud server on the premises. And the key here would be to make sure that all of these call the tests the same, to make sure that they end up in line with each other. And I mean, it's definitely a little bit more advanced, but what we could do is, for example, use barcodes or any sort of, I mean, if we have any sort of identification on the piece, we could actually tell by reading it with a little vision system, and it doesn't have to be an advanced vision system, probably a camera of maybe 2,000, 3,000 euro. And that could read that either barcode or serial number or whatever you tell it to read, and then use optical character recognition, put that in your spreadsheet, and then, I mean, the rest is up to your kind of computational speed. I mean, doing averaging is fast.
It's super fast.
But I wouldn't say, I mean, using this kind of method to automate and use those kinds of averaging results based to determine different ways in your production flow, I don't think it will be that fast.
No, no,
That,
not
yeah.
for different, not for separate them. But
Okay.
for example, let's pretend we have in the like we have a lot of requests regarding this kind of mining application when we work with a good particle size, for example, like
Yeah.
in cement. Yeah.
Yeah.
So we don't have a problems with the particle size there. It's less than 10 microns, so it's
Yeah.
like pretty homogenized, but still not enough homogenized.
Yeah.
And
Okay.
we don't want to separate it. We just want to increase the area of testing. So
Yeah. Yeah. I understand. So you want to have a couple of through repetitive tests.
True.
But the speed of using one arm and do repetitive testing would be too slow, right?
Not enough. Not enough.
Yeah. Okay. Because the other way I was thinking about your question, I mean, you can always use a simple vision system, a two-dimensional vision system, to determine like, here's the plate, and you have already predefined that if the plate is this size, then I want to test these different spots. So you could actually have determination of the patternizing automatic as well. So, and this doesn't have to be very expensive. So if you combine a cheaper, a two-dimensional vision system together with one of these force torque sensors, then the unit could actually look at your testing area, determine where the different pieces are, determine those locations, and then with the force torque sensor, search for each location. So you could basically have a big testing area, throw out all your samples, and then it'll test all of them.
Yeah, this is exactly. So for example, if we're talking about cathode production for batteries, this is exactly an application for these kind of things. So we have a layer, foils 30 centimeters, and the speed is quite, so even if we, for example, on the one arm, I don't know how much maximum weight one arm can handle.
12.5 kilos.
12.5. So if, for
so
example,
we could put on four. We could. Oh yeah, that's actually one thing we could do. We could put
4 units on the one arm.
Yeah, exactly.
Yeah. So this is really what I'm thinking about. Just and test, like, increase 4 time testing area, which is significant, and we can we're gonna save 10 seconds.
Yeah, but I mean, those cathodes, those are usually hanging, right? They're hanging on a transportation belt, right?
Different. No, it's sometimes it's also it's a case what you're describing, but for example, right now they more design it on the 3D printers. So this is just like a kind of A4, A0 size.
Okay,
paper,
so smaller cathodes.
Yeah, smaller cathodes, and they just come to this chamber. This chamber, as like a 3D printer, just printed them, and then they go on the quality control. And the speed is quite high, and they won't fully like remove human power. I mean, automate it fully. So
maybe, I mean, Vladimir, I'd say that I always like the robot arms, but I'd say probably you put 4 Vantas beneath a transportation belt, and the A4 sheet goes in, and then you shoot with the Vantas, and then it moves on, and then takes the next one.
I know. In my opinion, this is because this is still for robot arm, because I also like it very much, because it makes much more flexible for the clients. They don't need to fix something forever. They can do a lot of stuff. So even like James, absolutely right, pointed that we considered it previously with Fox IQ as this is something stationary, and you have to align everything with this unit, and now it's not. Yeah,
no, that's true. That's true. Yeah.
So yeah, thanks. I got answers. Thanks.
Thank you. Thank you. Are there any other questions? Yeah, Damian?
Yeah, Carl, sorry. Yeah, we were talking about alignment. Do you know if there is any optical sensor that could also help the robot to position itself?
You dropped out of the meeting when I talked about that. So there are. I mean, you can do 2-dimensional vision systems, and you have 3-dimensional vision systems.
Okay.
And you also have what's in between, which is called a 2.5D measurement system. So a 2-dimensional system uses just an XY mesh, and determines the rotational of parts and size of parts, etc. And it shows us like, okay, here's the part, And if we have determined and told the unit how it should be testing on those parts, then it can determine all the positions by themselves. So you can basically throw them out on a table. And if you compare that with either you can use these, easy proximity sensors looking more or less like this, which is just a laser, and you can actually tell the distance from the. So if you have a specific thickness of material all the time, then you can use these kinds of sensors, because it'll just go down to the actual height, and then you're done. The other way of doing it is using a 2.5D vision system, and the 2.5D does not only determine the height, the size in XY, it also determines the height of the part. It doesn't determine the 3D structure, but it determines the height. So then you'd have positions based on height and on size. The third way is using a 3D vision system, because if we have parts that are a little bit irregular, say a casting, for example, and you'd want to test the outside of a casting, and you always want the unit to go down perpendicular to the surface, then you'd need some sort of 3D vision system where you can determine, okay, where is my angle of propagation in perpendicular route to the surface, and you could do that also automated. So it just depends on your application and how much is worth. But if we look at a 2D vision system, I mean, it's not more than maybe 3,000 euros. If we look at a 2.5D, maybe we're up to around 5,000 euros. And if we go up to a 3D, yeah, then it can be really expensive, depending on your level of resolution, etc. But we're looking at 15,000 plus.
Okay.
So yeah. That's what you want to consider. How important? I mean, you always need to consider: is it a need to have or a nice to have? That's what you need to determine.
Yeah. Thank you.
You're welcome.
So I have another question, Carl. You mentioned this is one of the largest cobot arms with or at least the longest reach. Does that mean that there are smaller versions, or?
Yes, absolutely.
Let me explain. The reason why I ask is I've got a number of projects at the moment working with mobile robots, so like the Boston Dynamics dog, and others, specifically on drones, potentially on a drone. And I'm just wondering how feasible it would be to mount one of these arms on something like that.
So what you do is not mount them on any of those. You'd probably mount them on an AGV. So there's the sister company of Universal Robots called Mir, also from Odense in Denmark. They manufacture AGVs. So I don't actually know what AGV stands for. Do you know? Oh, okay. So AGV is basically a little automated moving robot, but it's 4 wheels and basically just moving around on your shop floor. And in Volvo, for example, you have those kinds of Mir AGVs with a cobot arm sitting on top. So they actually move around the factory and do stuff. So they have bin picking exercises where the operator needs a certain list of items. Then the AGV with the cobot arm and a little gripper tool moves into the place where they have all their warehousing. It picks everything up, and then it goes out on the factory floor to the operator. So that's absolutely a possibility. I mean, you have the UR10e, the UR5. Those are the UR10e can lift 3 kilos. You have the UR5, which can lift 5 kilos, and those are, the UR10e is 500 millimeters in reach. The UR5 is 800 millimeters in reach. Then you have a stronger one, which can lift 16 kilos, which is the UR16. Then we could basically mount 5 Vanta Ix's on that one, but that one has a little bit more limited reach. And then you have this one, which is 1300 mil, 12.5 kilos in payload.
Yeah, I'm thinking I can see lots of potential applications for kind of making the ARM and the Vanta Ix mobile, basically.
Yeah. No,
rather
definitely.
than being fixed on an ARM.
Yeah.
In a position. So no, it's very cool. Opportunities are endless, as they like to say.
Yeah. No, definitely. That's what so we had a fantastic meeting yesterday with like 70 customers, showing them all sorts of different applications. And what I usually say is, when you start talking about these kinds of applications, the only thing you know is you're going to come from a meeting like that with more ideas than you had prior to the meeting. And that's basically, I think everyone looking at this will have that feeling that, okay, I can use this in a lot of applications. Any other questions?
Not from my side, at least. Yeah.
Cool. I hope you enjoyed it. This is we've been doing quite a few of these kind of demonstrations on other products over the COVID period, but we realized that it's actually, even now when we can meet, it's quite convenient because we can show you so much at the same time, and you're all in different locations all over the world. So it's quite convenient. Thank you all for joining. James, good luck in Denmark.
Thank you, Carl.
Yeah.
One last quick question. Are we able to get a copy of the recording?
Oh yeah. So all of this is recorded, and it's put on YouTube. So, and I can send it to you as I sent before, like we transfer something on the raw file footage as well.
Yeah, please do so. Yeah.
Please.
Yeah, of course. Will do.
Okay.
So everyone have a great afternoon.
Thank you, Carl. Thank you for your
Thank you.
presentation.
Great.
Bye from Stockholm.
Great. Yeah.
Thank you very much.
Take care.
Bye-bye.
Ciao, ciao. Bye.